So I would like to thank the organizers for giving me this opportunity to speak to mathematicians. As you might know, I am a physicist, so I will try my best to make myself understandable, and I ask you to please stop me. Maybe not whenever, but every other time when you don't understand, okay? So I also would like to thank the organizers for their complete mastery of the weather. This way, no way anybody is going to go for a hike during lectures. That's really the best. Okay. So now that I have a captive audience, I can get started. So the title I chose for this series of lectures is a bit vague. So it doesn't have probability in it. And for a good reason. I'm not a probabilist myself, so I don't have really an approach of a probabilist. So even in as much as the vocabulary is concerned, I have sometimes trouble understand what you guys say. So you will certainly have problems understanding what I say, but we'll try to adjust, okay? Now, in this title, there are two words. Combinatorics is the simplest one to understand. Combinatorics, to me, is the pedestrian way of approaching many of the problems that occur in statistical physics, which all have to do remotely or closely with counting, okay? Now, what physics does usually in statistical physics is not just count, but count with weights, okay? So those weights, you can call them probability weights, or you can call them energies or activities or things which give a little bit more substance to your model, which describe a priori what kind of interactions you're putting into this melting pot. And then what you expect, of course, is out of a little bit of information you've put in your definitions to get out some interesting structures and results as to the global behavior. So this is my sort of way of approaching statistical mechanics is via this combinatorial approach, which has to do with enumeration. Okay? Now, integrable. What does integrable mean here? It could mean several things, but it has a very specific definition which dates back of the good old mechanics, actually. And so maybe I'll just introduce kind of vaguely what it means. There are two notions, fundamental notions, which are classical and quantum integrability. So maybe I should start with that. So basically, integrable systems deal with ways of describing evolution of physical systems. Okay, so you have certain evolution in time. Let's say you have a time, okay, and you evolve in time. And integrability is going to guarantee a certain number of properties of that evolution, okay? And it's a very strong constraint. So it doesn't happen naturally in nature, if you want. In nature, you take a random model, it's not going to be integrable. But the great thing about that is that it has all chances to be among the same universality class of many other models which are not integrable, okay? And because it is integrable, it's more amenable to solving, to actual solving. So there are actually two notions here. There's the notions of integrability and the notion of solvability. And sometimes even exact solvability. And these are two different notions. In classical mechanics, these two notions are very closely related because integrability sort of ensures exact solvability. But that's not the case in general, okay? So how to describe this in the simplest way, integrability? I would say it has to do with symmetries, okay? You imagine that you have a system, so an evolution, okay, and which has a sufficient number of symmetries that sort of restrict the phase space so much that you can actually solve it, okay? So in more precise terms, you would have an evolution equation governed by a Hamiltonian. Okay. Sorry. We are discussing classical integrability here. So in the classical case, where these little things, you probably know all about them, but it's called a Poisson bracket. So there's some structure under all this, Poisson algebra, Poisson brackets, canonical commutation relations between canonical variables. I'm not going to describe all this because this is just some sort of justifications of what will come next, and I don't think it's worth spending much time on the classical case. But basically, a symmetry here will be actually conserved quantities, or more precisely, quantities that commute or Poisson commute. This is called the Poisson bracket. With H. So imagine a set of quantities, C1, C2, etc., such that CIH, or HCI, well, I of course didn't define for you all the axioms satisfied by Poisson bracket, but it has to be skew symmetric, it has to enjoy a certain number of properties, among which the Jacobi identity. Okay? So anyway, if you have such a quantity, of course its evolution will be just that it remains constant. Okay? So that's why they're called conserved. So Ci are conserved quantities. And basically, as I was pointing out, the integrability of a system amounts to the existence of a sufficient number of independent conserved quantities. So it has to do with what the dimension of your Poisson manifold is, and basically, if you have half the dimension independent quantities, then your system is going to be integrable. Now, if you don't understand any of this thing, just think of the one integrable model that you all know about, which is motion in a central force. Okay? So the force applied to you is always directed to a fixed point, right? Now you start a motion like this with a force which is central. What happens? It stays in a plane. Okay? That plane is defined by the initial condition, Cauchy type conditions. Okay? Why does it stay in a plane? As a consequence of a conserved quantity, which is the momentum. Okay? Now, there's even better that can happen to this central force motion. For certain particular potentials of which that force would derive, you have even more conserved quantities, and you can get to something which is even better than an integrable model, which is called super integrable. Okay? But let's not enter in this, but okay, have this in mind. Okay? Conserved quantities as a consequence of how the model is defined, basically, and this is what you get. All right. So, okay, now the thing I will really be interested here is not this classical integrable system, but discrete classical integrable system. Okay, discrete means what? Means that my time now is going to be a discrete variable. Okay? And that basically my evolutions will just be sort of recursion relations in T, if you want. Okay, so an evolution okay? And the notion of integrability here will be extremely simple. It will be that if you define a certain evolution, let's say you give yourself a certain recursion relation, there will be quantities independent of T modulo that equation. Okay? So a quantity C independent of T in N modulo the evolution is this notion of conserved quantity. Okay? And basically, we are trying to mimic what happens in the classical continuum case, which is try to find a sufficient number of such conserved quantities that you can actually solve your model. Now, exact solvability, I was vague here, now I can say a bit more. As a consequence of integrability for these classical models, you have theorems, okay, which tell you that basically you can solve in a very simple way. That is, you can find some sort of change of variables, which are called action angle variables, in which basically the motion becomes just linear, right, proportional to t. So in this discrete case, there is no global theory of a discrete integrable equations. That's still missing, so that would be a really good program for mathematicians. But in all cases one can actually deal with, one finds the exact same thing happening. That is, you can sort of disentangle all the evolutions into just, by changes of variables, basically into just linear evolutions. Okay? So you're going to tell me, oh, well, this is completely trivial. Let's go over to something else, right? Well, to just drop an example just like this, the planar maps that will probably come up tomorrow in Mirmont and Le Gal's lectures actually are an example of such integrable evolutions. You just have to define what you mean by time, okay? And the time for them will be just the geodesic distance within the graph, okay? So you imagine you have a graph embedded, so it's called a map once it's embedded. You have a notion of a path from one point to another, from one vertex to another, okay? And the mean of the length of the path is this geodesic distance, okay? And we'll be able to actually derive recursion relations as functions of this geodesic distance, which will have this magic property of integrability, okay? And the planar maps seem to be sort of a machinery to produce for you such integrable equations, okay? But before I go into that, I want to give you another example, which comes from somewhere completely different, okay? And which I want to show you as a sort of a toy model and also pedagogical model, so that you just know how one can deal with those things and how one can go from just the stupefaction of having a conserved quantity to the actual solution, okay? So that example probably is too simple, but I think it has all the structure in it. And something I didn't mention, of course, is that at the end of the day, there will be combinatorial descriptions of the solutions. So the example of the planar maps is fun because you start with combinatorics, try to evaluate the number of planar maps with such and such conditions. You end up with some evolution equation in terms of this geodesic distance. You solve it, and by solving it, you find out that it involves other combinatorial objects, okay? So let me give you this example. Here is my example. A recursion relation, so T I will call N, okay? So here it is. Okay, I take the simplest that comes to mind. This would be it. Okay, so you view this as a three-term recursion relation. Okay, you have to supplement it with initial data. Okay, let's say n larger or equal to 1 here. Okay, and well, if you give yourself, say, R0 and R1, right, free term, you need to give yourself 2 terms. Okay, so that would correspond, if you want, to discrete Cauchy data, which is the value at 0, and the value of a discrete derivative at 0, which would be R1 minus R0. Okay, so these 2 data are discrete Cauchy data, if you want. And you ask the question, can I solve this equation? Can I find Rn as a function of R0 and R1? Okay, it's pretty simple. Okay, so how do one go about it? Of course, I already told you somehow the answer, but there will be some conserved quantity. So you can go hunting for conserved quantities. So in this case, if you look a bit at this equation, you will see immediately that it takes a very interesting form. It looks like a determinant equal to 1, actually. Okay, so let's write it in this way. You agree? I just pushed this guy on the other side. Okay. So let me call Wn this guy. So the equation of motion, if you want, my evolution, just tells me that Wn should remain constant. Okay. Of course, you all remember your old classes in differential equations, and you remember that one was always introducing the Wronskian of solutions when one was dealing with differential equations, let's say with linear differential equations with constant coefficients. And the fact that the Wronskian remained constant while you evolve the system was exactly the sign that there would exist such a differential equation. So you can think of this as a Wronskian y, because you see this is a determinant, so you could subtract the second column from the first, and then this would be a sort of discrete derivative, right, of r at point n. Okay? While here, this would be r at point n minus 1. Okay? So you see this is like the discrete Wronskian of two solutions which are just taken at two times shifted by 1. Okay? So that's why I want to call it discrete Wronskian. Okay? So what do you do with differential equations once you have your Wronskian, which is a constant? You take a derivative. Okay? So let's take a derivative. Of course, in the discrete setting, it means Wn plus 1 minus Wn. Okay? We use multilinearity of a determinant, and this is just Rn plus 1 plus Rn minus 1, and then Rn plus 1 and Rn equals 0, 1 minus 1. Okay? All right, so what do I learn here now? I learned that these two columns should be proportional, right? This is the vanishing of a determinant. So there should exist some constant c a priori depending on n, such that Rn plus 2 plus Rn, the vector, Rn plus 1 plus Rn minus 1, is Cn times the vector Rn plus 1 Rn. Okay? But this is two equations, right? So the first equation, notice that the indices of the r's in the top equation are the same as the indices of the r's in the bottom equation, shifted by 1. Okay? So it means that Cn should be equal to Cn plus 1, right? Because if you write the first equation and shift the n by minus 1, you will find that Cn is Cn minus 1. Okay? So C is independent of n. So this is my conserved quantity. Okay, so you see this equation is integrable. It has a conserved quantity, where in this case, because of a dimension of space, it's sufficient to be integrable. So the existence of one conserved quantity is sufficient here. Okay. All right, so now that I have this conserved quantity, what do I do with it? Well, of course, from here, I immediately see that Rn plus 1 minus Crn plus Rn minus 1 is equal to 0. So I end up with a linear recursion relation. Okay, so now it's over. You just look at the characteristic polynomial of the equation, right? It has two roots, x plus or minus. And then Rn should be a linear combination. Okay? Now, you can see here that I have these two exponents. Okay? What I was announcing earlier was that I had a possible change of variables in which the motion was just linear. Okay? So you can see that if you write these guys as exponentials of some angles, then these angles are going to grow linearly, and that is the manifestation of this integrability. Okay, so that's pretty simple. Huh? It's trivial. But, okay, so you have to solve this quadratic equation, you will have square roots all over the place. It's not very nice, but at least you can certainly write down everybody, like lambda plus, lambda minus, x plus, x minus, all as a function of your initial data, R0, R1, and you're happy because that's the solution. Okay. Now, here I want to just point out to you the combinatorics I was sort of alluding to before. So I claim that actually the solution of this system is extremely combinatorial, and that you can actually express in a much more efficient and beautiful way is the solution in terms of R0 and R1. Okay? Now, there is even a theorem, which is part of a much larger story, but I write it down for this equation. So the solution Rn to, let's call it star, and with initial data star star, is a Laurent polynomial of R0 and R1 with non-negative integer coefficients. Okay. Laurent polynomial just means polynomial of R0, R1, R0 inverse, and R1 inverse. Okay? It doesn't grow. Okay, it's quite surprising if you think just for a second about it. Imagine you know that Rn and Rn minus 1, both of them, are polynomials of R0, R1, R0 inverse, R1 inverse. Now, to get Rn plus 1, you have to divide out by Rn minus 1, right? So you have a gigantic polynomial here, another gigantic polynomial there that you divide out by, okay? And it turns out that there is divisibility, okay? So this divisibility is also some sort of a consequence of this integrability, and it's quite non-trivial, okay? So why do I say there is a more general story? The more general story is that actually this is the baby example. I'm sorry, I'm taking you to other mathematics, okay? This is no longer probability theory. This is more like algebra and combinatorics. But I think it's worth it that you know that we have connections with many, many different areas here. And somehow we're attacking from one little point of view, but there are many other points of view that can be adopted. And whenever you manage to compute something, then everybody benefits from it, okay? So it's a baby example of what is called a cluster algebra. So a cluster algebra is a sort of dynamical system. So again, we are talking about evolutions, okay? Now, in a cluster algebra, the evolutions will be able to go in many directions, okay? So you start with a Cayley tree. Let's say with a degree, fixed degree, okay, in my example 4, okay? So what it means is that, okay, and it never stops, okay? Right? You label the edges, so it's a Cayley tree with labeled edges. Let's say we embed it in the plane, and we label the edges clockwise, counterclockwise. So let's say this is 1, 2, 3, 4. 1, 2, 3, 4. 4, 1, 2, 3. 3, 4, 1, 2, 2, 3, 4, 1, etc. Okay?
When you say it's a Cayley tree, you mean it has to be a Cayley graph?
No, I just mean an infinite tree. Okay, I'm just looking at it from one vertex. Okay, and then I view it as a sort of infinite landscape in all directions, with branchings and branchings and branchings. Okay.
It's regular.
Yeah. Yeah. Okay. So. Now, at each vertex of my Cayley tree, I will have information, data, okay? So this data will be a vector of formal variables. So let's say, let me give a name T to this, no, T is no good. A to this vertex, okay? Then at vertex A, you will have a vector x1a, well, maybe x1 of A, x2 of A, x, say, n of A, no, 4 of A. Okay, so as you can notice here, the number of, the dimension of my vector is exactly the order of my Cayley tree. So Cayley tree of degree D, okay, with labeled edges. So then I have a vector, D-dimensional vectors. So this will be a rank D cluster algebra. As you can see, the rank is just the number of data I will have at each vertex. Okay, so I have this data at this vertex, but not just this data. I have more. I have also a skew-symmetric integer matrix, which is called the exchange matrix. You will understand immediately what it means. This matrix is going to code the evolution, if you want. Okay? So it's a way of coding the evolution. So I call it B of A also. Okay? So it's D by D. Same as the size here. Okay? So at each vertex, I have a data like this. Okay? And now I have to tell you how I go from a vertex to the next. Okay? So there is an evolution rule. And in that context, it's called a mutation. That is telling you how the data at a vertex are related with the data at a neighboring vertex. Okay? So you see around the vertex, you have as many labeled arrows as you have elements in here, right? Well, the label of the arrow will tell you which of the values here is going to be evolved. So all the values remain. So let's now go to a situation where I have A and B related by an edge labeled K, okay? And I have to tell, so at A, I have this vector, if you want, X of A, and this vector X of B, and then this matrix B of A, and this matrix B of B, okay? And I have to tell you how you go from one to the other, okay? And this is called the mutation, mu K. It will be involutive, so whatever you do takes you from here to there, it will take you from there to here. And here is the form it takes. So xi of A is xi of B for all I different from K. So as I was saying, the label tells you which of the components is going to evolve. And then xk of A, xk of B is equal to the product from I equals 1 to n of xi of A to the B I k plus.
Could you write a little larger, please?
Oh, sorry. So evolution. So here I told you that xi remains the same for I different from k, but for k, you have an evolution which is given by a product from 1 to n of xi of A to the bik plus, I will tell you what this is, plus product from 1 to n of xi of A to the minus bik plus. Okay, I told you that this matrix B, of A. I told you that this matrix B was skew-symmetric, okay? So this plus is just mean of max. Well, it's the positive part. Yeah. Okay. Okay. And there will be a companion equation, which I'm not writing. I'll let you think about it. Okay. Which tells me how B of A and B of B are related. But what I can tell you already is that mu K is an involution. So whatever makes you go from A to B should make you go from B to A. Okay? Meaning that here, B of B should be able to do the same job. Okay? So this is a big help. It tells you almost everything about this B. Okay? So you see a setting like this. Okay? So you start, a cluster algebra will be just defined by the data at a certain vertex. Okay? And everywhere else, it will be completely deterministic, determined by these equations. Okay? Neighbor to neighbor to neighbor to neighbor. Huh? Bon. What are the properties of such a construct? Well, first of all, it's a very interesting mathematical construct because it relates to many things. Okay, so to name only a few, it relates to the theory of Somos-like sequences, of which, if you want, this would be also a sort of baby example, and I will tell you in which way this is a cluster algebra. So this is a bit how everything started. It is related to the question of total positivity. The question of total positivity, I think it's also an interesting question for probabilists. You're asking the following. What is the minimal set of conditions you should impose on an n by n real matrix to guarantee that all its minors are positive? Okay? Well, you see there is a fundamental, really interesting property to this equation, which is that it doesn't carry any minus sign. Okay? So if something is positive here and here, the sum of two positive things is still going to be positive, so you are going to carry positivity along. Okay? So I don't tell you more, but it really has a big role to play in this framework of total positivity. So more interesting, even more interesting, and coming closer to our purpose here with enumeration of maps, it has to do with so-called Tashmuller space geometry, which is yet another way of looking at random maps, if you want. So I don't want to say more about it. But this is really a very active kind of subject now. So it was invented by Fomin and Zelevinsky. Invented and then perfected, because in the first case it was not quite perfect, but let's say from 2000 on. Okay? So why do I mention this in relation with this theorem here? Well, there is actually a theorem, a general theorem, about these cluster algebras. Well, you can ask the question, if I'm sitting somewhere very far away in that tree, at some vertex, okay, I certainly have variables which can all be expressed in terms of the initial variables here. Let's say this is my vertex 0, okay? This is where I start. I give myself data here, and I ask very far away, what does the data look like, okay? Well, there is a theorem which is a consequence of this particular evolution, which is that x at A is a Laurent polynomial of x of 0 for any vertex A in the Cayley tree. Okay? So this is sort of what dictated, actually, to these people how to write down this evolution. It's a non-trivial fact, but It's really what motivated them. Okay. Now, what is more interesting, of course, is that there is an open conjecture. I love open conjectures. And the open conjecture is that x of a is a Laurent polynomial of R with non-negative integer coefficients. So it's been proved in various cases, but there is no understanding, general understanding of that fact. Okay? Bon. Oh, okay. Laurent polynomial of the initial data. So it's a vector of variables, formal variables. Okay? It's a polynomial of those variables and their inverses. That's what is meant by Laurent polynomial.
That polynomial depends on which a you.
Of course. So you change a, you change the polynomial, but it remains a polynomial, which is amazing. Because you see, you have this gigantic polynomial here by which you divide, you divide by another gigantic polynomial, and eventually there is divisibility.
But now inverse. So why are you dividing with the problem?
Oh, because x itself is a polynomial. See, assume that you know that x of b, at b, I have a Laurent polynomial. Okay? Now, I want to prove it at a. Okay? So I express a in terms of b. Okay? I have to divide out. All right? So on the right-hand side, I have things which depend. Actually, here, the dependence on a, I can switch a for b because this mutation is involutive. Okay? So the formula for a is the same as the formula for b. Okay? So everything depends on b only here. But this is a huge polynomial divided by another huge polynomial. And I have this magical property of divisibility. Okay? Which is a consequence of all this setting. But more interestingly is this positivity and integer coefficients, which means that there is combinatorics hidden under this, which nobody really understands. But at least in this case, I understand it, so I will show you. Well, first of all, why I claim that this is a baby example of cluster algebra. So here's the claim. The solutions are n. So first of all, can be extended to n in Z. Okay? So I still have my two initial data, if you want, R0, R1. I write them vertically like this. Okay? And I can, of course, make this equation work to the right or to the left. Okay? Towards positive or negative times. All right? So I extend it to n in Z. And now, here is my Cayley tree. I claim that the cluster algebra corresponding to this equation is actually a rank 2 cluster algebra. Okay? So let me start from R0, R1 here. And from the following matrix, 2, minus 2, 0. Okay? So this is my B matrix, and this is my X vector, right? At this vertex here. Okay? Now let's say this is 1, this is 2, 1, 2, 1, 2, etc. Okay, this is my Cayley tree. It's a chain in this case. So the question is, what do the mutations do for me? Well, first of all, I didn't write down the evolution of B, but you will very easily find out that B has to evolve like this. So B is not really a problem. It just flips its sign. And as it's Q-symmetric integer, it remains Q-symmetric integer, so that's good news. And now what happens to R0, R1? Well, you see index 1 and index 2 refers to whether it's the first component that evolves or the second component that evolves, okay? I will make R0 evolve according to this equation. Because this equation, if you think just a little bit about it, is actually exactly this equation for the B matrix I have written. So, all right, so what is BIK? This is the kth column in B, right? So in the kth column, I read the positive part of the kth column as being the powers in the first term, okay? And then I read the negative part of the first column as being the powers in the second term. Well, I have a 2, certainly, in the first column, and a 0. So the 2 gives me this term, the 0 gives me that term. There is no term in the second term, so it's 1. Okay, so this gives me R2. Okay, now on the other side, it's the second component which is going to evolve. and it's not difficult to see that it has to be R minus 1. Okay, so the equation which is used here is that R1, R minus 1 is R0 squared plus 1. And the equation which is used here is R0, R2 is R1 squared plus 1, etc. So you can view actually this equation as being just the generic mutation in a rank 2 cluster algebra, right? So the toy equation okay. It's a cluster algebra. What about the theorem and the conjecture? We're going to prove both of them in this case, okay? By just pushing a little bit further what we just found out. So what we found out here is that there is this conserved quantity C, and that there is actually a linear recursion relation satisfied by the R's, and C is a function of R0 and R1. So let's compute C just for definiteness. So C is Rn plus 1 plus Rn minus 1 over Rn. Okay, now let me use the equation to eliminate Rn plus 1. Okay, and then I get Rn over Rn minus 1 plus 1 over Rn minus 1 plus Rn minus 1 over Rn. You will find that very easily by just substituting the equation into this. So you've gone from a three-term recursion to a two-term expression that has to be constant, okay? So in terms of differentials, you just integrated, right? But in a discrete way. Okay, so this is a discrete integral, okay? So now, of course, you can write it down in terms of initial data. Let's give names to these three quantities, y1, y2, and y3, just for definiteness. Okay, so my conserved quantity is y1 plus y2 plus y3. I have now this recursion relation. I will introduce the generating function for the Rn's. So generating function just f of t is sum of tn Rn, and here I go from 0 to infinity. Okay, from our series if you want. Now, of course, from the recursion relation, I know that 1 minus ct plus t squared times f of t. Well, okay, so the terms are killed far enough away from n equals 0. And you're only left, basically, with the two first terms, because starting from the third term on, everybody's killed. So you get something of the form R0 plus C R0 minus R1, minus T, right? It's just a first degree polynomial in T. So, well, then you can just express your generating function. So interesting thing here is to use y's as variables. So there is one thing you can notice immediately is that y1 times y3 is equal to 1. Okay? So y1, y3 equal to 1. And there is a coefficient 1 here. And I decide to replace 1 by y1, y3. Okay, it's no big deal, but so f of t is now, well, let me divide out by R0. It's 1 minus t, actually y2 plus y3 over 1 minus t, y1 plus y2 plus y3 plus t squared, y1, y3. It's another way of rewriting it. I used the fact that C is the sum of the three. This is R0 times C minus Y1. Therefore, it gives you this. Okay? So here, I already have a theorem, right? if I expand this in formal power series of t, I get polynomials of y's as coefficients, okay? And a polynomial of a y is a Laurent polynomial of a r's, right? Because each y is a Laurent monomial of a r0 and r1. So I get the theorem. Now, what about the conjecture? It should be a positive coefficient Laurent polynomial. So here you have to apply some physicist trick, okay? I claim that this is actually and I let you check it, okay? So, of course, once you have this, 1 over 1 minus something is just the sum of what something to the power n for n equals 0 to infinity, right? So it's positive. So you expand this, it's positive. You expand this, it is still positive. And you expand this, it's still positive. So the positivity follows completely from just formally expanding in powers of t. So conjecture follows. Okay, and now when you see this, you immediately think about paths. So the solution is actually a generating function for paths. Okay, so this is more like an interpretation of a solution if you want. Rn is the, well, I will use this term now, partition function for paths on a segment 0, 3. Okay, by that I mean just paths with integer increments, with increments plus or minus 1. Okay, starting and ending at 0. Okay, and with weights, which are going to be these y's. So first of all, 1 for each step, 1 per step of the form I plus 1. Okay, I equals 0, 1, 2. And yi per step, I plus 1 to, no, I to I minus 1, I equals 3 to 1. Okay? Well, in other words, you can immediately interpret this continued fraction as being the generating function for paths that can go only up to height 3. Okay, so these are paths in a strip, okay, which start at 0 and end up at 0. So these are Dick paths, but in this case, it's completely truncated. It cannot go above this height. And now whenever you come down from a certain height, so the heights are here, 0, 1, 2, 3, okay? So whenever you come from a certain height, you descend from a certain height, you remember by putting a weight, y index the height from which you come. So here you have y1, y2, y3, y2, y2, y1. So the weight of this path is just the product. Here y1 squared, y2 cubed, y3. Okay, and the partition function, which is classically called z, but here it's Rn, is just the sum over paths. I didn't say, and of length 2n. So sum of our paths from 0 to 0 of length 2n of the weight of paths, right, which is this product along the path of all the collected weights. Okay? So this should be clear from this continued fraction expression. You're building up your path from the bottom, if you want. So, Ah, yeah, sorry. Okay, let me go to the other side. So you're building your path from the bottom. So you look at the first steps. You will have steps that go up from 0, like this, a certain number of them. Okay? So this stands for the 1 over 1 minus ty1, if you want. You put as many y1s as you like in that form. Then in between any two of these, which will be the descendants of this y1, you put as many y2s as you like. Same thing here. And then in between any two of those y2s, you put as many y3s as you like, which gives you y3. Okay? Okay, that's it. So here is the proof of this positivity conjecture in this particular case. Okay, so I've been carried away a bit far from my purpose here, but I want just to show you an explicit, completely explicit example of how integrability somehow trivializes everything, and on top of that, allows us to have some combinatorial interpretation in terms of paths. Paths with weights. Paths on a target graph with weights. Okay, remember this because this is something which will pop out many times. Okay? So this is all I wanted probably to say on this classical case. Yeah. So there are many other, of course, examples of such classical discrete integrable equations, but there is no real theory of them. Okay? So it's more like a zoo so far. But in that zoo, some particularly remarkable set of objects in that zoo will be provided by the planar maps and their dependence on geodesic distance of marked points. Okay? Yes?
This example is someone finds some integrability, kind of integrability of lax, pair of lax.
Yeah, okay. So the notion of lax pair, of course, you can define lax pairs for discrete systems, definitely. Yeah.
But
In this case, not that I know of. Well, it doesn't look necessary to me because you have the exact solution here. But yeah, I believe it's possible. Yes. Yeah. Okay. All right. So now I want to discuss a little bit quantum integrability. So we're still going to describe evolution, but now of quantum system. So now the setting is operators acting on a Hilbert space. Okay? And you will have a particular operator, which you will choose, which you will call the Hamiltonian, which will generate for you the translations in time. Okay, so in the continuum, it's again something like, so now I call it O because it's an operator. dO over dt is H commutator with O. So now you think of those guys as operators acting on a Hilbert space, and this is the commutator now. Huh? Okay, so the same notion, of course, is that a symmetry of my system will be generated by an operator which will commute with a Hamiltonian. Okay, so you still have this notion of a quantum conserved quantity. Probably more than just a finite number of them, which commute with the Hamiltonian of my system. Okay, some classical examples are the quantum spin chains. But okay, I don't want to throw at you all these names. I prefer to give you some explicit example in which you really see what's going on. Okay, so let me not describe this any longer and go into the example I wanted to discuss here. So basically, so this is one-dimensional, of course. but one-dimensional quantum. So you have an evolution in one dimension, okay? But you're evolving operators. So there is a very interesting way of viewing one-dimensional quantum evolution as actually two-dimensional classical evolution. So here is the way. You look now at lattice models. So this is getting closer to what has been discussed so far. So a lattice model. Take your favorite lattice model, percolation, okay, on the square lattice, bond percolation, okay. Look at it in a particular geometry, let's say on a rectangle, okay, with whatever boundary condition you like, okay. And there's a way of generating configurations of whatever system you're looking at on such a portion of lattice by deriving some sort of recursion relation. So let's say you have defined your model by its degrees of freedom and the energies you're attaching to them, or basically which weights you have to put to occupied bonds or non-occupied bonds, or bonds that are close together or far away from each other. You put different energies to that. So you have a certain definition of your system. And now there is a way basically of generating. Okay, these don't match, of course. All right. Configurations of your system by describing what happens if I add up a row, let's say, to my rectangle. So I had an n by L rectangle, and now I add a row of 1 by L. Okay. So a priori, I had a certain number of let's say, site variables or bond variables that are occupied or not occupied, okay? So the state of sites or bonds along the line will be actually the labels of vectors on my in my Hilbert space, okay? Then I will, to add up one row, I just have to sum over all possible intermediate configurations here with, again, fixed configurations on the new bottom I'm putting, okay? So this is exactly a matrix product, okay, on that Hilbert space, acting on that Hilbert space. So this is called the transfer matrix. So it's really a matrix acting on that Hilbert space whose vectors, I say again, are indexed by the configurations of a given row, okay? So act on vector space in which vectors, it's a sort of canonical basis, if you want, indexed by configurations of a row. Okay, so now I view these matrices as the matrices of operators acting on this Hilbert space. And I see that if I call Zn the partition function here, so sum over all configurations in this rectangle with boundary conditions here and there, well, I have something like Zn plus 1 is Tn, well, T times Zn. Okay, loosely speaking, I can generate my configuration on a slightly larger rectangle out of those on a one less. Okay, so it's like a recursion relation. So I want you to understand the construction of those lattice models as the result of applying repeatedly some recursion relation. Okay, so this way it looks a bit like this other approach. Okay, so that's one thing. Now, what is quantum integrability going to mean in this context? So, in the classical case, I needed sufficiently many conserved quantities, that is, quantities which would commute with the Hamiltonian, and I didn't say, but commute also with each other. Okay, so they're called in involution. And in a case like this, things are more complicated because you expect somehow to have an infinite number of degrees of freedom in the thermodynamic limit when size grows, or the mesh goes to 0 and the size remains finite. So the notion here is replaced by the existence of an infinite number of conserved quantities and actually in most of the cases they will take the form of just a parametric set of transfer matrices where T belongs to some segment, let's say. So an infinite set of transfer matrices that commute with each other and that commute with the Hamiltonian, which would be the T at a particular value of that T. So let's say T equals A equals really the transfer matrix of my initial system. But I have a one parameter family of such transfer matrices that all commute with each other. Okay, so why is it interesting and why does it help solve the system? Okay, what do I mean by solve the system? Well, I mentioned earlier the thermodynamic limit. So you want to be able to say things on your system when the size grows infinite. So you see that if you have an expression like this, let's say we put some specific boundary condition on top and on bottom, let's say periodic, okay? Then you would have something like Z big N is trace of T to the N. That's a possibility, right? That's if I had put on top and bottom periodic boundary conditions. Okay, but you could choose any boundary conditions you would like, and then instead of being a trace, it would be maybe a T sandwich between the top and bottom state, or whatever sums of states you want to consider. But the important thing is that the parameter that governs the size of a system here appears only as the power of a transfer matrix. Okay? So imagine you have a way of knowing that the transfer matrix is diagonalizable. Okay? Then you would know for sure that such a quantity is dominated at large n by the largest eigenvalue of your transfer matrix. Okay? So diagonalization of a transfer matrix is the one thing that is going to save you lots of pains here because it will allow you to immediately get properties at large sizes, okay, out of a definition of an operator which is at perfectly finite sizes, you see, by just iterating it a large number of times. So diagonalization of T is the solution. If you can diagonalize T, you have your solution. Okay, at least it's good enough for me. Then, of course, if you look at more refined properties, like correlation functions, how does the occupancy of a site here relate to the occupancy of a site there in percolation, for instance? Then you have to work a little bit more, but what is really interesting is that, again, it's by looking inside the spectrum of your transfer matrix that you will find answers. Okay, so you find many, many answers by just looking at the spectrum of a transfer matrix, by diagonalizing it. Okay, things like correlation lengths, things like tests of conformal invariance of whichever model, all this can be done by just analyzing how in the large both n and L limits the eigenvalues of a transfer matrix behave. Okay, so it's very important to have a way of making sure I can diagonalize my transfer matrix. And then, so if you want, integrability will guarantee the fact that you can do it. An exact solvability will be whether or not you can actually do it, okay, explicitly. So the existence of a parametric set of transfer matrices is extremely good because it means that all those guys, if they are diagonalizable, have to diagonalize in a common set of eigenvectors. Okay, common eigenbasis. Okay, and this is a very, very, very strong condition, which most of the time is sufficient to ensure exact solvability, provided you have certain hints on what the structure of the eigenvector should be, etc. Okay, so now instead of waving my hands, I will give you an explicit example, which I believe should resurface later on in this school, which has to do with dimers. Okay, so here's my example. So it's sort of a dual of the dimer problem on the triangular lattice. So I will introduce it slightly differently, but I pronounce the name dimers already. So it's the rhombus styling of the triangular lattice. Okay, so I start with a triangular lattice with equilateral triangles, like 2 dimensions. Okay, and I'm going to tile a certain domain of that lattice, so I pick a domain. Okay, I don't take a random domain because it has to be tileable. Okay, so I will tile that domain, provided it's tileable, with 3 types of tiles, which are basically adjacent triangles. Okay, so here are my 3 types of tiles. I will have a yellow tile, orange tile, and blue tile. Okay, 3 types of tiles, and I want to tile my domain. Okay, because we are doing physics, I'm giving some weights to these 3 tiles, A, B, and C. Okay, and you can ask the question, well, in how many ways can I tile a given domain? And better than that, with a fixed number of blue, fixed number of yellow, and fixed number of orange tiles. Okay, so by just putting those weights, you can count actually how many of each tiles you have. Okay, so my claim here is that I can put this problem in the form that I described sort of vaguely here. Okay, and that this will be actually an integrable, a quantum integrable lattice model. So how does it go? Well, let me now fix geometry. So again, we're going to look at something like a rectangular portion. Now we are on the triangular lattice, so triangles and rectangles don't agree very much. So what I'm going to do is deform my triangular lattice in such a way that it looks like a square lattice, but with a diagonal drawn on each square. So do you agree to let me do this? I know it's not very beautiful, but at least it's much simpler to draw. Okay, so this is my triangular lattice. I just pushed it a bit, and now I can look at a rectangular portion of this, of size L by whatever, M. Okay. So I have a tiling in there. So it means now, okay, so I have to be careful that the blue tiles, so you see I have pushed things like this. So now the blue tile is a square. Okay. The yellow tile is made of 2 halves of squares. Maybe it helps if I put the missing edge here. And finally, well, the C is even more C. So it's something like this. Okay, with this vertical. Okay, so I just deformed things a little bit. Okay, so now I'm going to do exactly this. That is, concentrate on a strip inside this domain. So we just zoom in on a strip. Assume I have a tessellation, a tiling. And I concentrate on the strip. Well, I didn't mention, but I think it will be much simpler for us if you wrap this rectangle around the cylinder. Okay? It just means that this will be identified with this. Okay? This edge with this edge, this edge with this edge. Okay? I put everything on a cylinder. So cylindric boundary conditions. It's not very restrictive, but it will make our life simpler. So let's do it. Okay? So now I concentrate on one strip in here. Okay? So what do I see on that strip? Well, I claim, okay, so let me redraw the strip. So this is the underlying lattice. And now on top of that, I'm going to put some tiles. So let's say I put C tiles. So this is like the bottom half of a C, right? So I should continue it like this. And the top half of a C, okay? No, of a B, I'm sorry. So this is a B tile, this is a B tile. And then somewhere I'm going to put an A tile. Okay. And then I continue, I put some C tile again. And then after the C tile, I will put a B tile, and then I put a C tile. Okay, and the B again, etc. Okay? So what you see here is actually sufficient upon gluing to generate all the configurations of tiling, you see? So this realizes exactly this sort of dream here of a transfer matrix generating for you all the configurations, okay? So my transfer matrix, now I have to describe on which vector space it acts, okay? On which Hilbert space. Now, let's look at an horizontal line here, okay? And I see that basically two things can happen. Either the edge is in the middle of a tile, therefore it's not there, right? It's unoccupied, if you want. So I put a 0 when it's not occupied, okay? Now this blue edge, it is occupied by the edge of the tile, so I will put a 1. This orange edge is also occupied by another tile, so I put a 1, but this is empty again. I put a 0, okay? So the claim is that my vector space, actually, vector space is the span of, well, sequence 0, 0, 1, 1, 0, 1, etc., with zeros and ones, okay? So I can, if you want, have a notation. So E would be my canonical basis, and the indices are those vectors of configurations. Okay, so this is the basis of my Hilbert space. Okay? Now, what is remarkable here in my model is that if I have a certain number of occupied edges on this row, I will certainly have the same number of occupied edges on the lower row. Why? Because these guys are tops of tiles, okay? And both the blue and the orange tiles have an edge on their top and an edge on their bottom. So the edge propagates to the bottom, right? There is therefore conservation of the number of occupied edges. So the number of occupied edges along horizontal lines is conserved. So this is the first feeling of integrability we have with this model, is that there are some conservation laws. Okay, so let's say it's K. So then I have a vector space Vk, which is the span of E, let's see, N1, N2, and L, such that Ni belong to 0, 1, and sum of Ni from 1 to L is equal to K. Right? So this is my vector space of total occupation number K. Okay? And what happens to the transfer matrix here is that it's an operator acting on that space, I mean on the, a priori on the big space V, which is the direct sum over K over Vk's, okay? But it actually splits into blocks, okay? It's a block diagonal matrix, if you want, and it has blocks only connecting Vk to Vk. So there is a block structure already of my transfer matrix. So you see the conservation law is reducing basically the complication, right? It's making life simpler. Okay, but that's not over. It's much better than that. So what is T? I have a vector space here. Now I have to describe what is T. Actually, there is a different way of indexing those guys, which is much better. Because you see they have k ends, which are equal to 1, and all the others, which are equal to 0. So instead of giving the whole list of ends, why don't we just tell where the ones are? Okay? So it's just another way of writing the same basis. But now it will be EX1. Well, I shouldn't use the same. Okay, I use the physicist notation of bra. Okay, bra and ket. So this is a ket, X1, X2, Xk now. It has only k informations. And this k information, so this Vk is also the span of those guys. Now, such that X1 less than X2 less than Xk larger or equal to 0, smaller or equal to L minus 1. Okay? And these are just the positions of the ones. Okay? So either you give the list or you give the positions of the y's, but it's the same space. Okay. What is T? So let me introduce the shift operator at I, Si, which takes the vector xk to xi plus 1 xk. So it's really the shift of the ith index by 1. Okay. Well, I claim then that T is just the product from 1 to k of A plus C Si. Sorry, times B to the L minus K. Okay, so what is this? I want to view the K, think of K as being small compared to L. Okay? So I have only a finite number of conserved horizontal occupied edges, right? Meaning that I have those tiles that sort of propagate from the top to the bottom between the blue and the oranges. So let's say, let me just show what it would mean for a macroscopic configuration. Sorry?
The blue is invisible.
Ah, the blue is invisible. Aha. So if I promote blue to white, will it be okay? All right, so let's promote blue to white. That's too bad. Bon. Okay. Etc. Okay, so that would be 1. Then, let's say next to it, there would be another 1. Etc. Okay, so imagine your tiling, you can decompose it by being blind to the yellow. Okay, I should have chosen blue for the yellow. It would be easier to be blind to it. But let's just blind out the yellow. Okay, so what we see is these configurations of tiles, and you see whenever an edge is occupied, the edge below it must be occupied, or the edge after it must be occupied. So this is exactly this. A is the weight for whenever the occupied edge induces another occupied edge at the same position. It's an A. And C is the weight when you have an edge occupied at position alpha, let's say, and the next at position alpha plus 1. Okay, so it's this shift operator which sends this configuration to that which has a guy shifted by 1. Okay? Yes?
So the definition
Yes?
If xi plus 1 is equal to xi plus 1.
I was expecting that question because you're putting your finger where it really is painful. This is wrong. This entire thing is wrong. Precisely because of what you mentioned. So actually the problem is that, you see, I could go from two occupied edges, which are one after the other. Okay? One would be a white square, and the other one would be an orange tile. And this, of course, is not allowed. No way. Okay? So there is something wrong with what I just described. Okay? But there is an extremely simple solution. And the answer is called fermions. Okay? So fermions are guys that don't like to be next to each other, like French neighbors. You know? They hate to be next to each other. So this shouldn't happen. So make them hate each other, and it won't happen. Okay? So I just extend the Hilbert space to allow now not just strictly increasing sequences of x, but also weakly increasing. Okay? But I add the condition that whenever xi is equal to xi plus 1, then the corresponding vector is 0. Okay? So I put by hand the fermionic condition that you hate your neighbors. Okay? You hate to be too close together. Okay? Now, if I work in this set instead of in the other one, now this is the correct statement. Okay? Thank you for asking this question. So, well, we're almost there. Now, we have this transfer matrix, which depends on these three parameters, A, B, and C. Okay? And remarkably, this is a three-parameter family of transfer matrices. Of course, there is a dependence which is kind of trivial, which is that of, you see, it's really projective somehow. If I multiply each B, A, and C by the same number, I will get just a lambda to the L in front. So I actually only need to use ratios. So I could divide out everybody by B, or equivalently, set B equals 1 without loss of generality. Okay? So we can just get rid of B, and then T is just this product of A plus CSI. Okay? So we have now a two-parameter family of transfer matrices, and I should perhaps put a K just to indicate, well, no, I don't really have to. I can consider them all at once, all the blocks, all the K blocks at once. But so here is the nice, really nice property that all these guys commute with each other. Okay? The shift operators, of course, are these trivial operators that commute with each other. So I have a commuting family of transfer matrices. This is a quantum integrable system. Okay, quantum integrable. And in the 6 minutes left, I will show you also that it is exactly solvable. Okay? So the question is now diagonalization of T. Yeah, I realize I mentioned the word dimers, and I never showed the dimers. So the dimers are on the dual of a triangular lattice. Okay, a dimer is just a bond between two neighboring vertices. Okay? And such a bond, again, there is a hateful process here, but whenever a vertex is taken by a bond, it cannot be taken by any other bond. Okay? So bonds repel each other. Just again like these fermions. There is a, but all the vertices are occupied by a bond. So they're everywhere. Okay? So if you want to view it in terms of the tiles, the dimers are just the sort of middles of those tiles. Okay. So let's diagonalize T now. Okay, so from the existence of a infinite commuting set of transfer matrices to the diagonalization, there is in general quite a lot of work. It's not completely easy. But in this case, things turn out to be beautiful because the transfer matrix itself is just made out of a shift operator, right? And we know very well how to diagonalize the shift operator, right? The diagonalization of a shift operator, SI Z to the xi is Z times Z to the xi, right? So this is the diagonalization of a SI operator. So therefore, as I have a bunch of SI operators from 1 to k, I'm just going to consider test vectors of a form product Zj to the xj, right? And of course, if I apply my transfer matrix to such a vector, I will find product of A plus C Zj from j equals 1 to k of the same vector. Okay? So this is the eigenvalue. But of course, my problem here is that this vector doesn't belong to my vector space. My vector space, I recall, has been altered a little bit. These are the x's that are weakly increasing, but such that whenever 2 equate, then I get 0. And this is certainly not the case for this product. But there is a very simple remark, which is for any sigma in Sk, any permutation sigma, I can use the vector, which is as well. Yes? Z is a complex number. Xi is an integer, and z to the power xi. Well, z to the power xi is a function of x, okay, of x1 up to xk, and the shift operator on that function shifts xi by 1. Therefore, okay, it's just a shift operator. So I can as well apply a permutation sigma. Okay, so this is called a plane wave. Okay. Now I can apply the permutation sigma, and you see it changes nothing. It will give me just the permuted product here, but it's the same. So same eigenvalue for this different eigenvector. So I have actually many eigenvectors for the same eigenvalue. But I need an eigenvector which, whenever two of the x's come together, vanishes. Okay? Well, there is only one in that set, which will be just the sum. So my vector, finally, the eigenvector, I should call it psi, maybe. Sum sigma permutation of signature of sigma, product zi sigma y. Okay. Well, of course, this is the determinant. Right? And as such, of course, the determinant is going to vanish whenever two columns, in that case, become equal. Okay? So two x's being equal means two columns equal, and my determinant vanishes. And you will check that in the linear combinations of all these vectors, this is the only valid linear combination that will belong to my space. Okay? So basically, this is called the Slater determinant. Okay? The Slater determinants are the eigenvectors for the tiling transfer matrix. So it's really a good reason for calling them fermions, because Slater determinants are known to be wave functions for fermions. Okay? Well, so it's over, because now I have my eigenvector, my eigenvalues. Okay? And I just have to impose whatever boundary conditions I had on my model. In this case, the boundary condition is just the fact that I wrap things on a cylinder. So it means that this quantity should be defined modulo L in terms of xi's. Okay? And you will see very simply but this definition modulo L implies an equation for these, for the ZJs, which is that each ZJ should satisfy this equation. So this has a very famous name, such an equation. It's called the Bethe-Ansatz equation. And actually, the fact of looking for eigenvectors as linear superposition of plane waves is called the Bethe-Ansatz. In this case, the Bethe-Ansatz works, and this is sort of the basic case in which you can explain the best these diagonalizations of transfer matrices. So I think I'm going to stop here and let you think about this a little bit. Okay? And next time, we're going to stop this aspect and go into the classical discrete integrable systems hidden behind the planar maps. That will be the next and probably part of the session after. And then we are going to look at quantum systems, okay, in relation with various combinatorial problems and probability, asymptotic probability problems as well. And hopefully this will cover the last sessions. Thank you. Yes? Okay. So I have written notes on this magic computer, and I think I can create PDF out of them, but it's big PDF. So I will give a copy to the organizer, and maybe he can print it or do something with it. It's really big. I don't know why I have a PDF converter which creates enormous files and which are not supported by email. So it has to be given in hand. But if you have a computer, I can no problem. Do you have questions? Yes?
I have a question. So the shift operator and the transfer matrix are operators on these spaces VK.
Right.
Suddenly over here, there's some mysterious Z that I don't understand.
Oh.
The shift operator is acting on. That doesn't look like an element of VK. So what is going on?
Okay. What's going on is that I am actually considering the shift operator on a different space, okay, which is now functions of the xi's, okay, rather than these cats. But it's isomorphic. So, sorry? I'm sorry. Yeah, it's in the completion of a space. It's isomorphic.
So what is the isomorphism?
So basically, I'm looking at functions f equals 0 as soon as xi plus 1 equals xi with okay, and then I have these boundary conditions that things are defined modulo L. So these are basically the eigenvectors for the shift operator as functions of only the variable xi. Okay, so I forget about the other variables. So what are the eigenvectors of the shift? They are of this form. There's only this. Okay, I write them as z to the power xi. I should maybe write them in exponential form, but that's what they are. Okay, and then I'm just now looking at. Think of this as sort of Fourier series, if you want. This is the best way, right? It's like Fourier series. Okay, so you look for a combination C x1 xk product zj xj.
So this is the same thing that's going on in the course on noise sensitivity.
Yeah, Yeah.
You're doing Fourier
Yeah.
analysis on...
Absolutely. Yeah, it's another way of saying it. Absolutely. Yeah. Yeah. It's like doing Fourier and these are just so it's zi to the xj over ij. It's a determinant ij between 1 and k. So you have a collection of k z's, okay, which all must satisfy this equation, okay? And so what does it mean? It means that z is a certain exponential 2i pi over L. I mean, you can write explicitly what z's are. They are indexed by integers, okay? And the thing is that those integers are defined modulo L, and they must be distinct, because, of course, whenever two z's are equal, you're going to get 0 again. So if you want non-trivial eigenvectors, you will have to list all the possible z's solutions to this equation, indexed by integers, which are strictly increasing. Now, strictly increasing integers on 0L, it's exactly what we started from. So it's the dimension of my space. The dimension of my space is just LK. And I'm saying that basically the number of solutions here is the dimension of the space. So I get an independent set of eigenvectors which saturate the dimension of the eigenspace, so of the space. So this is diagonalization. Yes?
So the division of that equation comes from the fact that we don't understand.
Yeah, in this case, it comes from the fact that from the boundary condition, basically. And this is the sort of simplest Bethe-Ansatz equation you could think of. Normally, there's more interaction. I don't know if you've seen any of those, but usually you have a nasty product on the right-hand side. So this is like the case 0 of Bethe-Ansatz equation, if you want. After that, you have to work a bit more. You have to extract the largest eigenvalue. So largest eigenvalue will be largest value attained by this. So you have to discuss according, these are on a circle. So you have to discuss according to where, in which locations is this product maximal, etc. So there is still some more work to do, but I just wanted to show you one example of what this quantum integrability and exact solvability could mean. Yes. Yes.
Isn't there a problem with commutation of the transfer operators to do by this fermionic thing? Because you can shift one over and it dies, or you can shift the other one and shift it over?
Okay, so what might be necessary is that you extend actually your space to any x's, not just the weakly increasing, but all the x's. But you still impose this condition of vanishing whenever two are equal, okay? And that's sufficient actually to restrict to just the determinants.
But
So
I'm sorry, I would say
that would include your case. But sort of, you see, you can only go to the right here. You cannot go to the left.
But if I'm saying, like, let's start with like a concrete vector, like x1 is 1, x2 is 2.
Yes?
If you shift the first one over,
Yeah.
it hits, and then you're a 0 by that fermionic.
No, but there is no tile like this. Do you mean this?
No, I'm just saying you might have two of them, and you have to move one out of the way before the other one hits.
1, 2. Okay. So you say,
One can move over while 2 is still there.
so 1 moves over while 2 is still there. Yes, this is what we want to, and you see.
If 2 moved over first, 1 can move over.
Oh, first, you mean, you're thinking of an order.
Yeah.
An order, no, but there is no order. We're just looking at the configuration, the global configuration of a line, okay? We're not like flipping one and then the next and then the next. We're just looking at a configuration. And some configurations are forbidden, okay? And you just want to impose the fact that the configuration is forbidden, and this is what you do here. I'm sorry, I didn't get your question. Yeah. So this is the forbidden configuration. There's no question of the order in which you get to it. Yes? Good question. Actually, you see, this model is kind of nasty because it is critical already. So it is a phase transition by itself. It is at a phase transition by itself already. Okay? But now you can move along with these parameters A and C. So it's actually a priori, an entire family of critical models. But that, okay, it would take us really too far. But I'm pretty sure people discussing dimers will come back to this. So you'll probably learn more. Thank you.